Welcome to Lecture 5 of Part 2 of the course Introduction to General Relativity. As you know, Part 2 is titled Mathematical Preliminaries, and it is intended to equip you with the tools from differential geometry and Riemannian geometry which are necessary to work in warp spacetime, that is spacetime with gravitational fields turned on. This is also the 7th week of the course, so this is Lecture 5 from week 7. Or 42nd lecture overall. Alright, so the main reference for today's lecture, which is regarding calculus and manifolds, is Nakahara's text. I'm using 2nd edition, so the relevant material can be found in chapter 5, these pages. And Carroll's lecture notes in general relativity, 2nd chapter, these pages, as well as Hockney and Ellis, chapter 1. These pages cover a similar amount of material and be considered as alternative references for this lecture. As usual, the lecture notes for this lecture will be posted on the NPTEL website. And those who want a bit more detail and a bit more depth can consult Werner's excellent text on differential geometry. Although I must caution that this is not a physics book, this is a grad level mathematics textbook. Alright, I'm going to assume the following background material. I'll assume some familiarity with the idea of a manifold with or without boundary. I'm going to assume familiarity with the idea of coordinate charts and atlas of a manifold, in particular the maximal atlas. And I'm also going to assume familiarity with the notion of a transition function between charts. As you know, when coordinate charts are the same thing as what we in physics we say coordinate systems. So transition functions are the maps which take you from one coordinate set of coordinates to the other set of coordinates. So these represent passive coordinate transformations or general coordinate transformations in the language of GR. I'll also assume some familiarity with the notion of a smooth map between manifolds. So all these were covered in the previous lecture. So please look back at the previous lecture if you don't remember these. And I'm also going to assume some familiarity with ideas from linear vector spaces, LVS for short. That is the notion of a dual space and dual basis. And I'm also going to assume familiarity with the Einstein summation convention for indices, that is repeated indices or dummy indices, are to be summed over all possible values of the indices, and they can be relabeled anytime. On the other hand, free indices are not to be summed over, and neither can they be relabeled. All right, let's look at the agenda for today. Our aim is to become familiar with the notion of smooth functions and curves on a manifold, which will then enable us to define vectors as linear differential operators. And the associated notion of a tangent space, we will discuss a different basis for tangent space. And finally, the transformation law for components of a vector. Then we will introduce the idea of one form as linear functionals from the tangent space of the real line and the associated vector space, which is known as the cotangent space. We will discuss different bases in cotangent space, and we will also look at the transformation laws for components of a one form or covector. Finally, we will look at generalization of vectors in one form, which are rank PQ tensors. Again, these are multilinear maps which map you from P copies of cotangent space and Q copies of tangent space to the real line. This is also a vector space, which will have bases, which will review. And finally, we'll write down the transformation rule for components. All right, without further ado, let me begin the lecture proper. So, calculus and manifolds. First concept you define in calculus is that of a function. So, I will always ask you to have in mind the calculus of a n variable, the calculus of n real variables, and always contrast whatever I'm saying with that analogous situation in the calculus of n real variables. All right. First is the notion of a function on a manifold f, which takes you from the manifold to the real line. Okay. So if p is a point on the manifold, then f with the argument p will give you a real number. So f of p is a real number. So you have some manifold m, and this is the real line, set of real numbers. Then f takes you from the manifold to some point on R. Okay, so That's why we call it a function. Instead of, so contrast it to the case of multivariable function of n variables, where you take the function in Rn, point in Rn, and then you map it to a real number. So that would have been f with n real variables. Here instead, what we have is an n-dimensional point p in an n-dimensional map. Okay. So as I said, every time try to compare it to the analogous situation in n-variable calculus. Right. Now the manifold point p must lie in some coordinate system, u comma phi. Phi is the coordinate function. Then phi of p will give you the coordinates of the point p. So I'm using a shorthand notation. This x is actually a shorthand for the n components, x move. So you can write it in this set builder notation. So it's a set of n real numbers, x move, where moves take value from 1 to n. Okay. All right. So we can use phi of p to denote the coordinates of the point p. And since phi is a homomorphism, we can invert this to get p as a function of the coordinates of p. The phi inverse of the coordinates of p will give you back p. All right. So this is useful because f of p, I can write substitute p as phi inverse of x, and then I get a composite map f of phi inverse of x. So f of phi inverse I'm going to call f tilde. So we have f of p, this real number f of p is same as this real number f tilde of x. But what is f tilde of x? Well, f tilde takes as an input the coordinates of the point p, which is an element in Rn, and then it gives you a real number. So f tilde is a map from n real variables to R. So it's a function of n real variables. So this is what I meant. So we converted a function, we started from a function on a manifold and we obtained a function of n real variables. This is how we will set up calculus on the manifold. We will, every time, we will use the coordinates of the point p, x, as a proxy for p itself, and then the notions in calculus on a manifold boil down to notions of calculus of n real variables. So, okay, this is just a function. We need to define what is a smooth function. F is said to be smooth if the corresponding function f tilde, then f is said to be smooth. So f tilde define c infinity for real variables is already known. Continuous c, as you know, c infinity means functions which are continuously differentiable for all derivatives. So every kth order derivative exists and this continues. Okay, so the smooth function set of all smooth functions are the set or space of all smooth functions is denoted by curly f of m. And we can define a smooth curve on a manifold. So this is the real line, this is the manifold, and corresponding there is a map such that each point on the real line is mapped to some point on the manifold. And the locus of all these points on the manifold are said to be a one-dimensional curve. Okay? So the fourth point is here, and then we generate some kind of curve on that. Okay? So if t is the curve parameter, so t is this real line parameter, sometimes known as the curve parameter, then c of t, so c is the map, so c is this, which takes you from the real line to the manifold. So c of t is p, some point p. So t is this value on the point on the real line, and c of t is this point p on the manifold. P can be represented by its coordinates of p. So p is same as phi inverse of x, where x is the coordinate of p. And then if we take phi of both sides, this phi inverse, we get rid of this phi inverse, and we get x. So phi of phi inverse of x is just x, is equal to phi of c. Okay, so we get a composite function. So the coordinates become some functions of R. So again, we have successfully mapped this curve on a manifold to a curve on Rn, because the coordinates x live in Rn. So, and this t is R. So this establishes a map which is the curve in Rn. So every curve in manifold is actually mapped to a curve in Rn. And then we declare this curve on the manifold C to be smooth if the corresponding, if x of t is a smooth function of the t's, okay? Infinite order, all order derivatives exist and they're continuous. So the family of, or the set of all smooth curves on a manifold C are said to belong to the space chi of M. I mean, I've written X, but this actually should be big chi of M. All right, so once you define a function, the next natural thing to define in calculus is the notion of a derivative or differential coefficient of a function. And as you know, in multivariable, for example, you have done in vector calculus, the derivative is not unique. Derivative depends on the direction in which you want to measure the rate of change of a function. So a direction has to be specified. How does a smooth function f change as we move along some smooth curve C on a manifold? So we have some manifold M, and there's some smooth function f is given, and we want to find out how f is changing as we go along some curve C. Okay. Now, so this will lead us to the definition of a derivative of a function as a point P lying on the curve. Okay, how do we see that? Well, we'll do a little bit of math. So f of p is the real number, and p lies on the curve. So if I change the curve parameter, the p will change, and f of p is also changed. So this is what I want to measure: how f of p changes when I change the curve parameter as I move along the curve t. Okay, so d of fp of by d of t. So f of p is the real number. So it's a well-defined quantity. Okay, evaluated at the point p. Okay. Now f of p, as we saw in the last slide, the function f of p, I can replace it by f tilde of the coordinates of p, f tilde of x. And when x lies on the curve, the point p lies on the curve, that means the x are themselves functions of t. So we have this derivative to be derivative of a composite function, f tilde of x of t. Okay, so we have to apply chain rule. So for x's have to be first taken derivative. So f tilde is directly a function of x. So we have the derivative of x tilde with f tilde with respect to x. And then the x's themselves are functions of t. So then we have this derivative of t with respect to t. And notice here I'm using the summation convention because the repeated index mu is actually summed over. Okay, this is x is actually n real variables. So that's why we have defined partial derivative. We use it using a partial derivative. And of course, x's are functions of a single variable t. That's why we have normal ordinary derivative. Okay, this dx mu dt or x mu dots, these I will call v mu. Okay, so this is v mu multiplied by del mu and then some overall mu acting on f tilde. So v mu times del mu, and because it's a repeated index, it's actually a sum over mu. This I'm going to denote by big B, and this is an operator. In quantum mechanics, you're used to putting in hat. You can put a hat, but I won't put the hat, just B. So this is a linear differential operator acting on f tilde. Okay, v mu times del mu, which acts on L tilde. Or we can write B is an operator which is acting on f tilde. Now, by abuse of notation, which is widespread in differential geometry textbook, this is denoted by V of f, not f tilde. Although technically speaking, v mu del mu acts on f tilde and not f, but the way due to abuse of notation, this is denoted as v is acting on f. But keep in mind, when we write v acting on f, we actually mean v is acting on f tilde. All right, so this linear differential operator v mu del mu with mu summed over all mu is called the tangent vector of the curve C at t. And this is very easily, you can see the analogy with Rn here. In Rn, if we are given, for example, R3, if we are given a curve, we know then each of these, so this three-dimensional vector, this will be a function of t, and the tangent at any point is given by the components of x vector dot t gives you the tangent vector. This is precisely similar notion. Dx mu dt, the derivative of the coordinates, that times. The only new thing to notice is the basis element. Instead of using ijk, we are using del mu here. Other than that, it is exactly the same notion as in calculus of Rn. The derivative of the coordinates components give you the components of the tangent vector. And the basis is a bit curious, del mu. So this is how we do in linear in differential geometry. When we say a vector in differential geometry, vectors are actually linear differential operators. Okay, a vector is a linear differential operator. Okay, so this is called a tangent vector. If, in particular, if the vector is given by the component is given by the derivative of the coordinates, then of course it's called a tangent vector to a curve. Okay. Now, imagine all possible curves passing through a point P. So this is the point P. There is some curve, and this curve has some tangent at this point. And then consider all possible curves passing through P. And all of these curves are going to have their own tangent vectors at the point P. Now, all these tangent vectors actually lie on they're members of a vector space, which is called the tangent space at P. The name is very well motivated because indeed it is the place where the tangent vectors live, so that's why it's a space of tangents. Okay, so it's very easy to show that these will be vectors, as you can check. If I take two tangent vectors, x1 and if we take two curves, x1 of t and x2 of t, and then I can show that their tangent vectors will be x1 dot of t and x2 dot of t, and then the linear combination will define a third curve, which is, let's say, some linear combination alpha 1 x1 plus alpha 2 x2 is a new curve whose tangent vector will be a linear combination of the tangent vector of the first two curves. So it's very easy to show that these form a vector space, linear vector space, LVS, and that space is called the tangent space. Again, I would compare this situation with calculus in Rn. Remember, differential geometry is a generalization of the Euclidean geometry of curves and surfaces, smooth curves and surfaces embedded inside R3 or R2. So, for example, in R3, you can consider a sphere, S2, which is lying inside R3. And then, most of you know that all the curves which are passing through a point on the sphere, the tangents will lie on this tangent plane. Okay, at this point on the sphere, you can define a two-dimensional plane, and all the curves passing, those vectors will lie on this tangent plane. So this tangent space is actually a generalization to that idea. As I mentioned, the only new thing probably is the basis vector, which is the differential operator W. Okay, so the basis vectors for this. Let's go back to the previous slide. Here, as I've denoted, V mu times del mu is the basis vector or basis element. How many such basis elements are there? There are n because there are n coordinates. So the dimensionality of this tangent space is seen as the dimensionality of the manifold. Now, of course, in P might be covered by a second coordinate card or a second coordinate system. So in a second coordinate system, we will use the second set of coordinates, x prime. And corresponding to that, we might have a second set of bases for the tangent space at that point, which would be given by E mu hat prime, which are the del mu prime. So remember, these are del prime is a short form for del x prime. Mu. All right. So these give you a second set of bases. And knowing the transformation rule between the bases, we can find out the transformation law for the components. So let's work that out. Very easy. So the vector doesn't change, its components and the basis has changed, but the vector itself doesn't change. So it doesn't matter which coordinate system you use. So V mu del mu should be the same as V prime mu times del prime of mu. And then what you do, this is the differential operator, so it is meant to act on some quantity. The quantity which you should act on is, let's say, x prime mu. Okay, you act both sides on the same quantity, x prime of mu. As you can see, derivative of del prime mu on this will give you the Kronecker delta. On the other hand, this will give you some kind of Jacobian element. Okay, so that will give you the transformation law for this tangent vector or vector. Now, as you can see, this is something which you will recognize as the transformation law for a contravariant vector, something which has an upper index. Okay, because the Jacobian element, Jacobian of the transformation from one coordinate to the other x prime is appearing. So in most old GR books, this is given as the definition of a contravariant vector. But that's not how we are proceeding in this course. We are setting up differential geometry from scratch. we introduce the tangent space and then the coordinate basis for the tangent space. Remember, the coordinate bases are these coordinate partials. So in tangent space, the coordinate partials are the basis elements. So once you establish the coordinate partials as the basis element, this transformation rules follows immediately as a result, not as a definition. Okay, so again, let me define a smooth vector field. Now this vector field v mu is actually a function of p, but then we can use the coordinates of p as a proxy for p itself. So v mu of x, a function of n real variables to n real variables to Rn. Okay, so if these are C infinity functions of the x's or x mu's, then V is said to be a smooth vector field. Okay, so smooth vector fields, the set of all smooth vector fields live in this space which is called gamma of n. And then there is finally the associated notion of a tangent bundle, which is some terminology you should be familiar with. Now consider the full manifold, not just one point on the manifold. Now at one point you define a tangent space. Now we consider all points P and consider the union of all such tangent spaces at each point. This union is given a name which is called the tangent bundle. So TP of M, union of all overall points P on M, gives you T of M. T of M is the tangent bundle. A smooth vector field can be thought of as a section of a smooth vector bundle on M. Although I'm not going to cover different geometry of vector bundles on this course, I just wanted to say it's an alternative way of thinking about a smooth vector field. Okay, next we want to define one form that are covectors and the associated notion of a cotangent space. Now, one form that defined to be linear functionals omega, which take an element of the tangent space, that is a vector, and map it to the real line. Okay, so something like this. Omega as an argument takes input a vector field, and then it spits out a real number. Omega of v is a real number. So such kind of maps in which the argument is not a real number, we call functionals instead of a function, because we are putting in a vector, a list, which is a list of n numbers, instead of a single real variable, square bracket instead of parentheses to define it. And we will call it a functional. Okay. Now, what do you mean by linear functional? Well, if I give such a argument with alpha 1 is a real number and alpha 2 is a real number, and v1 and v2 are two vectors, then omega of this, now this plus is a vector sum. Remember, this is not an algebraic sum. v1 and v2 are vectors, and alpha 1 and alpha 2 are real numbers. So this is a vector sum. Omega of the vector sum is equal to the algebraic sum, alpha 1 times omega of v1 and alpha 2 times omega of v2. I can give one example. For example, omega of v could be defined by one such example would be something which gives you the second component of v, something like that. Okay. So this would be, as you can check, this is a linear function. If I give v1 plus v2, or u plus v, u and v are 2, the answer will be u2 plus v2. So this is going to be a linear function. So this is an example of a one form. So one forms. Now, in addition, we impose some condition which will allow this space of one forms to be converted into a vector space. And these two properties are scalar multiplication and vector addition. How do we define them? Like, consider three such real vectors, real numbers, alpha 1, and alpha 2. These are real numbers. Then we define scalar multiplication of a one form, alpha omega, to be such that the action of alpha omega on a vector v is same as the normal algebraic multiplication of alpha with omega of v. So then define scalar multiplication. And similarly, we can define a vector addition. If I take two one forms, omega 1 and omega 2, the vector sum acts on v in a way such that it is equal to the algebraic sum of the actions of omega 1 v and omega 2 on v. Okay, so that will define vector addition. So this plus sign here is a vector sum, and the plus sign here is a algebraic sum. So this product is scalar multiplication, and here this is just normal algebraic multiplication of two real numbers, alpha and omega. So these two properties will convert the space of one form at a point P into a linear vector space, which is known as the cotangent space. And because This is the definition of a dual space, most of you know. If a vector space V is given, the dual space is defined to be the space V star. V star is the space of all linear functionals on V. And so T star P of M is the dual to the tangent space. Okay. So I can draw some kind of a diagram which will help things at this point P. You have the tangent space and then cotangent space. Okay, this is a second or a different vector space which is dual to the tangent space. T sub P and then T star. So the union of all such cotangent spaces of all points on the manifold is naturally called the cotangent bundle. Now, let me introduce a very special class of one-forms. By the way, I wanted to mention one-forms are also called covectors. So some people use the term covectors, so one-forms and same as a covectors. So an example of a one-form is the differential of a function. Given a function f, we say df to be a one-form. And how do we define df, or in particular the action of df? Well, that is given by this definition. So this triple equal to means it's a definition, it's not an equality. The left hand side is an abstract object which is being defined on the right hand side. So dff acting on V is same as, or is defined by the number v mu component multiplied by del mu of f and then sum over mu. Okay, so this is how you define differential of a function as a one form. Now in particular, I can choose f to be anything, so why not be the coordinate? So f of p will give you the muth coordinate of p. So that is the map from p to a real number, so it's a function. And now so I can define d of x mu to be a one form, because this is a function and then d of that should be a differential of a function. This is a one form. Now let's feed it, instead of v mu, let me feed this vector which is identity times del nu. Okay, the component is 1 and the basis element is del nu in the direction of del nu. And let's feed it to dx mu. What do we get? Well, this rule says the component is 1 times del nu of x mu. Okay, so that will give you the Kronecker delta. So dx mu of this vector gives you the Kronecker delta. So if you remember from vector space, the basis and dual basis obey this relation. So if E mu is the basis and theta mu is the dual basis, then the duality condition is given by this mu, which is given by delta mu. So for the coordinate differential and the coordinate partial obey exactly this kind of relation, hence we declare the coordinate differentials to be a dual basis to the coordinate partial, which is the basis for the tangent space. Okay, so the cotangent space coordinate basis is given by the coordinate differential, while the coordinate basis for the tangent space is given by the coordinate partials. Okay, so this is the duality condition. So that means any one form you can expand in this basis. So this is the basis element and this is the real number which is the basis coefficient. Okay, now we can do an exercise to evaluate omega of v in some basis. Of course, the final answer is, the final number you will get is basis independent, but it's good to see how what is the expression for this omega of v in coordinate basis. The way it proceeds is you write omega in this basis, you write v in this coordinate basis, and then because the one form acts linearly, this v mu, this number will just go out, and then you're left with this. You can use the condition to here, that will give you this omega mu multiplied by v mu, and then sum over mu is already implied because it's a repeated index. So this is the coordinate representation of omega acting on v. The final thing is to look at what happens if I go to a second chart, a coordinate chart. which are not necessarily these coordinate x. Instead, I go to x prime. Okay, so this is the general coordinate transformation x from a chart x. I'm going to x prime, where the x prime is some smooth functions of x. So then omega of v should be independent of the basis, so this should be the same. From these, we can easily surmise from this equation, and we know how v prime mu, how to write v prime mu in terms of v mu's. If we write that, we get the transformation rule for the components of a one form. As I've said before, you can recognize this transformation rule of components of a one form as same that of a covariant vector in books. There they define the covariant vector with this rule, but in our case it's just a consequence of choice of the coordinate basis. Okay, the last thing which I wanted to mention is that in vector space, you must have heard of this idea that the dual of a dual is the original space. Then star of the V star gives you back the original space. So the space, remember what this duality means. It means you look at all linear functionals of this V star, and that is actually V. So that means V, you can write V, it can, and feed it a one form, that will give you a real number. In fact, this is the same real number as omega if you feed V to omega. Okay, omega you can write phi, and then you can feed V to omega. But usually we don't do this in differential geometry, because usually if you remember when we define derivative of a tangent vector, we actually vector fields took as arguments some kind of function. Yeah. Okay, not a one form, but as I said, you can also put in a function. You put in a one form because the dual of a dual is the original vector space. All right, let me go to the generalization of vectors in one forms, which are tensors. Now, PQ rank tensors, these are multilinear maps from P copies of cotangent space and Q copies of the tangent space to the real line. Okay, that means it is an object. T is an object which has P plus Q slots. So total number of slots is P plus Q, in which you have to put total number of slots or arguments, and each argument you have to put either a vector or a covector. Okay. So, in particular for a PQ rank tensor, you need to put P covectors and Q vectors, but in a specific order. Okay, you cannot do it in arbitrary order. I'll come to it in a second. But the idea is that order has to be maintained. Maybe the first one is covector, the second one is a vector, the third one is another vector, and the fourth one is a one form, so on and so forth. This is how. So P plus Q total slots out of the P are for covectors and Q are for vectors, but they have to be put in certain order. That has to be defined. That is a part of the definition as well, which order you have to enter. And so I mentioned that these are multilinear maps. That means they're linear in all the arguments, all of these arguments. If you put a vector sum of omega 1 plus omega 2, then this T of that will split up into the algebraic sum of T of that omega 1 plus T of that omega 2. Okay? So it's linear in all arguments. Now, as you can guess already, that if I supplement this definition with the laws of scalar multiplication and vector addition, that is, if I define a scalar or real number multiplying T acting on these arguments, the same as the algebraic product of this number alpha with this real number T acting on all these arguments, and that defines scalar multiplication in the space of T's. And if I define the vector sum, this plus is actually a vector sum. Vector sum of two tensors, two PQ rank tensors with some arguments is same as the algebraic sum of T1 acting on those arguments plus T2 acting on those arguments. Then we have a notion of a vector addition. As a result, the space of all PQ rank forms get turned into, that space gets turned into a linear vector space, which we denote by this. P subscript of P of M, because it is located at the point P or associated with the point P, and because it is a vector space of P, Q tensors, so we have this in the notation. Okay. Now let's come to the basis. It's a vector space. Now we have to talk about components and basis. So one can show a PQ rank tensor in coordinate basis looks something like this. There's a real number, which is the basis coefficient or the component, times the basis element, which you can see is this tensor product or direct product. The same as in vector spaces, which you learn of taking direct products of vector spaces. This is exactly the case. So P coordinate partials and Q coordinate differentials. Now these order, let's say all these are, the first P are all coordinate partial, that is tangent space. Then the component will have those P indices up. And similarly, if you have basis elements which are differentials, corresponding component will have indices at the bottom. Okay, the one form indices are at the bottom and the vector indices at the top. Order has to be maintained, so I have taken a very specific order. So under a general coordinate transformation, so the tensor is the same, but we are using two different bases to write down the same tensor. So we have this equality, and from the transformation law of the del prime mu's and the dx prime mu's, we can write down the transformation law from the tensor. It's a very simple exercise. You should do it. And that the idea is that transformation law is such that for upper indices, on the right hand side, you have p factors of the Jacobian for a PQ rank tensor. Transformation law involves p number of factors of the Jacobian and q factors for the inverse Jacobian, x prime over x, and these are x over x prime, so inverse Jacobian. All right, so this is the linear transformation law. This is the famous transformation law, which in many old books defines what a PQ rank tensor is. I don't think this is a very good way to define it, because what you will observe is that this equation involves only real numbers. So there is no order. You can write the Jacobians in any order and it's the same. So this way of writing is insensitive to the fact that in a rank PQ tensor, the basis elements appear in a very specific order. And so this is not a nice way. According to me, I think a better way is to write the basis. And then automatically from the basis transformation rule, we can surmise what is the transformation law for the components. All right, let me give some examples. Vectors are actually a special case of a tensor. It's a 1, 0 rank tensor. One form of covector is a 0, 1 rank tensor. And the most important protagonist in our course is the metric tensor, which is the rank 2 tensor, rank 0, 2 tensor. So 0, 2, that means it will have direct product of two cotangent space bases. This is cotangent space, first cotangent space, and then direct product with another factor of the cotangent space. It's u. So this is rank 0, 2 tensor. Okay. Right. So these are tensors which will play an important role. Vectors, covectors, and the metric tensor. In old-fashioned terminology, these are contravariant vectors, covariant vectors, and the metric tensor. Same, of course. So let me summarize what we did today. We introduced the idea of smooth functions and curves on a manifold. We learned how to define vectors as linear differential operators. We understood what tangent space is and what are various bases of it, various coordinate bases, which are given by coordinate partials. And then we learned the transformation law for their components. In fact, we derived it. Then we introduced the notion of one form of covectors, and the covectors populate a vector space which is known as the cotangent space. We learned the bases, in particular the various coordinate bases for these cotangent space, which turned out to be nothing but the coordinate differentials. And finally, we wrote down the transformation law for the components in the coordinate bases. Finally, we looked at generalization of vectors and covectors, which are tensors, PQ rank tensors. We wrote down the basis component form, and then from that we deduced the transformation rule for the components. In the next lecture, we will try to define induced maps, push forward and pull back, which are very important in generality. We'll define integral curves of a vector field, of a smooth vector field, and the associated notion of a Lie derivative. Finally, we will talk about differential P-form, which is a special class of antisymmetric rank P tensors, which will, and then we will try to integrate them. So the notion of integration is associated with differential forms. Try to define. Thank you very much. We'll stop here and see you next time.